So first of all, anybody have any questions from last time? Or anybody have any questions on the practice problems getting ready for the test? Okay, so the test, exam 1, is next Thursday. Oh, that'd be the 23rd. And for topics, let's go up through particle kinetics. So today we're going to finish talking about particle kinetics, and then we're going to move on to rigid body kinetics, and that stuff won't be on the test. That'll be on the next test. And like I said just a second ago, get this in the notes, there aren't going to be any more quizzes posted until after the exam. I'll put the lecture and videos and notes up, but just you don't have to take any more quizzes. Okay, so let's go back to this problem that I gave you at the end of last time. The practice problems are meant to be just the difficulty of the exam. If anything, a touch harder than the exam. In the practice problems, there are a couple calculations that'll take longer than I kind of want you to take on calculations in the exam. But yeah, like the idea is if you go through those problems, know those problems sort of backwards and forwards, understand why each decision was made at each step in those relatively small number of problems. That's all I want you to know for the exam. Okay, so, yep. Is it going to be like the vector problems as well? There aren't going to be any vector problems, yeah. The vector stuff just comes up in everything else. So yeah, there won't be any directly vector problems. So just differential equations, kinematics, and particle kinetics. Any other questions? Okay, so we had a pulley over here, a cable connecting these two boxes. The top one's 2 kilograms, the bottom one's 5 kilograms. The 5 kilogram box has an instantaneous velocity this direction. There is a 50 Newton force applied this way. And we have friction. There's a coefficient of friction between the boxes, kinetic friction, of 0.2, and a coefficient of kinetic friction between the 5 kilogram box and the ground of 0.3. Okay, so this is a problem that, a lot of times you can sort of look at the problem, see what's going on without really kind of thinking about following any careful steps or anything. Your brain just, you've done enough problems that your brain just sort of does it. But this is one that can be tricky and sort of makes you go through the steps. So let's start by drawing free body diagrams of the two boxes. Oh, and we want to calculate the acceleration. So calculate the acceleration of the 2 kilogram box. Okay, so a free body diagram of the 2 kilogram box. Well, I mentioned before, the way to think about this is, so draw the outline. We know that gravity is acting on it. So we have a force downward of 2 kilograms times 9.81, so 19.62 newtons down. Move that out of the way a little. Okay, and now we're just going to mentally go around the outline of the body looking for places where other objects are contacting it. So start over here, nothing, 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 and then the cable's touching. So the cable's applying a force this way. We'll call that T. And then nothing, nothing, nothing until we get to the bottom and there's contact with the 5 kilogram box. Okay, so what does that contact look like? What do the forces look like? So one thing we could do is just treat it as a force vector, but we're going to have to simplify that later. So yeah, what does that contact do? What forces? There's a normal force, so call that N, and then there's a friction force that's opposite the. This is kinetic friction, so it's going to be opposite the relative motion of those two bodies. So if the 5 kilogram box is sliding to the right, the 2 kilogram box is sliding to the left. So the force of friction has to be to the right. Okay, and that's equal to 0.2 times N. Okay, any other contact? That's it for that one. So let's write Newton's second law for this, and then we'll move on to the second one. So Newton's second law says you got T0 plus 0, negative 19.62, plus 0n. I'm going to move this down. Plus 0.2 n0 is equal to the mass 2 times, I'll call this the acceleration of the 2 kilogram box, 0. So how did I know to express the acceleration like this? Yeah, you know it's not gonna jump up. It's not accelerating into the other box. It's not jumping into the air. You know it's going to move horizontally. Outside of that, how did I know it's going to accelerate in the positive x direction? I don't, but it doesn't matter. The signs will tell us the direction at the end. Okay. So we didn't use anything here that used that subscript notation, right? But notice that this vector, the sum of the normal force and the friction force, that's the total force vector that's applied to the 2 kilogram box by the 5 kilogram box. So this whole thing together adds up to be our force vector F on 2 by 5. And that means if we if we later come up with a vector f52, we know that the components have to be equal and opposite to that. Okay. So now the free body diagram of the 5 kilogram box. Oh, so one other thing. So nothing else is contacting this, right? What about that 50 Newton force? Yeah, that's being applied directly to the other body, right? So that's going to appear in the free body diagram and Newton's second law of the 5 kilogram body, but that doesn't appear anywhere. Like the effect of that only comes through those contact forces. Okay, so we have, for the 5 kilogram box, the 50 Newton force. We have the force of gravity, which is 49.05. We have this cable tension that has to have the same magnitude as this cable tension because of the pulley. Is anybody hazy on how I knew those directions for that cable? The direction of that force? Okay. So if you guys are totally comfortable with that, then keep doing what you're doing. A lot of times, if these get complicated, I think people find it easier if you think of isolating a body that's not just the block, but the block plus a tiny little bit of that cable, just some vanishingly small bit of the cable. So our free body is actually this, a little umbilical cord. And then the force applied by that cable comes directly out of that stump. Okay, and that always works. So here, same thing. And it'll help you always get those directions right, never flip the directions the opposite way. Okay, so now, say we started over here, or let's see, I didn't really go around, but we have that 50 Newton force, we have this cable force. If we're going around this way, we know that there's contact with the ground, right? What's the form of that contact force with the ground? Yeah, it's the same as the other one. I'll call this, I don't know, N2. And then there's a friction force in the opposite direction of motion. Yeah, so if this has, so this was something that, you brought this up at the beginning. We have the 50 Newton force here. We can tell that the acceleration of this box is going to be to the left because of that force. You can't always just eyeball problems like this and tell, but in this case you can. But the velocity is to the right. So which one matters for choosing the friction force direction? The velocity is what matters. So if the velocity is to the right, that means we have a friction force like this. Call that FF2, which is equal to 0.3 N2. And then if you keep going around, there's also contact with the 5 kilogram box by the 2 kilogram box. Okay, so there's two ways to think of this. You can think of it as the force F52, right? Or you can think of it as, since we already drew these two force vectors as known directions with scalar variables associated with them, we can just flip the directions of these two things. Okay, so that means that we have what was an upward force here is now a downward force with the same variable, and what was a rightward force here is now a leftward force with that same variable. the key to using this is that you only do it in the cases where if you did give it that subscript notation, all you're doing is flipping the subscripts. Okay. Yep.
If you were to do it with the subscript notation in one vector, would you like first calculate the angle from your other?
If you know something about the angle, then just always write it with the known direction and the variables. And then I think this isn't a bad way to do this. I do this often in my notes. So draw it as a known vector direction associated with the length, with the magnitude. Use those to express your vectors. And then just group, remind yourself what the subscript notation would be for these vectors, down here. So like this is the force onto by gravity, This is the force onto by the cable, So each of these, no matter what notation you're using in the free body diagram, each of these can be represented in that subscript notation. And it's sort of a way to check what you're doing in these problems where things get confusing, like this one. There's a lot going on, and it's easy to get confused.
So, like in static, a lot of times, or sometimes you want to just make that as one vector if you're doing like an equilibrium problem or something like that. Or a triangle. So is it in dynamics? Are you saying it's easier a lot of times to leave them as two separate vectors?
You mean combine them like these two into a single vector that says? No, either way, whatever you're comfortable with. I mean, if you added these two up, then you just, your force vector F25 would be 0.2 n. It's the same thing. Okay, so any other contact? I think that's it, right? So now Newton's second law says negative 50, 0, plus 0, negative 49.05, plus 0, n, 2, plus negative 0.3, n2, 0, plus, where am I? T0, plus 0, negative n, plus negative 0.2 n, 0, is equal to the mass times A50. So this is the external force. This is the force on 5 due to gravity. These together are the force on 5 applied by the ground. This is the force on 5 by the cable. And this is the force on 5 by 2. Okay, so if you're just trying to look for anything you can to check your work, here's your F52. These components have to be equal and opposite to these components. You get that if you switch the directions of those vectors correctly. If you do it in a case where that doesn't hold, though, you'll see your mistake here. Okay, so we have 4 equations. How many unknowns do we have? T, N, A2, N2, and A5. So we have 4 equations 5 unknowns, which means we need one more constraint equation. That doesn't introduce any new variables. So what's an assumption we can make about this problem that we haven't made yet? About the motion of this thing. Think about, so let's assume that this cable is not flexible in any way. You know, then there's a relationship between the positions, velocities, and accelerations of the bottom and the top, right? Like if the top accelerates to the left, if the bottom accelerates to the left, the top has to accelerate to the right. And there has to be a relationship between those two, right? So our constraint equation says A2 is equal to negative A5. And that constraint is going to come up with cable problems like every time you have a cable problem. There's something, so, I mean, if they're all moving around this pulley, the acceleration of one is going to put restrictions on the acceleration of the other one. Yep?
What sort of cable would be pushing rather than just...
None.
Okay.
Yeah.
So I'm trying to visualize it.
Oh, what's happening? Okay. Yeah. Okay, yeah. So if this one's accelerating to the left, right, it's pulling the cable. So this part's getting longer, you know, and that's making this part get shorter, and that's pulling the 2 kilogram box to the right.
But the 2 kilogram box and the 4 kilograms is going to the left. So that would imply that the 5 kilograms is pushing the cable and pushing the 2 kilograms.
Well, okay, so it's like this. So why is that? The position, the x position of the 2 kilogram box is equal to the x position of the 5 kilogram box plus some constant, right? That makes sense, right? Like, I mean, if you move this one a foot this way, it has to move the other one a foot the other way, right? And so if you take the time derivatives, you get this. The velocities have to be, I forgot that sign. So the velocities have to be equal and opposite. Same idea again, says the accelerations have to be equal and opposite. So the velocities, okay, so what you're talking about is two different things. There's a velocity relationship and there's an acceleration relationship.
I get mathematically how
Okay, yeah.
like I get
yeah, you just can't visualize what's happening.
Yeah, I'm having trouble understanding how a box is hooked to a cable moving to the right. The box on the left is pushed by said cable to the left.
Yeah, so it's not the velocity on the top.
What?
Shouldn't the 50 Newton force be on the top box?
Yeah, because it maybe was an instant before that.
Mm-hmm.
You created that motion.
Yeah. So, okay. So,
our friction force for our 5 kilogram box is to the left, meaning that the 5 kilogram box is sliding to the right.
The 5 kilogram is sliding to the right because, yeah, we said at that instant its velocity is to the right.
Okay, so the 5 kilograms sliding to the right,
Mhm.
then does box number, the 2 kilogram box on top, then get pushed to the, like move to the left, like either something
Okay.
fixing it.
Okay, so before the instant we're looking at, there was a 140 Newton force to the left on the top box. Okay. And that got everything, and that was applied for half a second, long enough to get the things moving where the bottom box is moving to the right and the top box is moving to the left. And that all happened because of tensions in the cable, not because of pushing on the cable.
Yeah, I didn't mean to pick it apart.
Yeah. No, let's get this kind of stuff straight as much as we can. Yeah. So does that make sense? I mean,
Yeah.
think of,
Yeah.
so then semi-independent of that, I mean, really entirely independent of that. Now at this instant, all those old forces stopped and we apply this new force of 50 Newtons. That force has the effect of slowing down the top box, right? Which applies a tension on that cable, and that tension on the cable slows down the top box. So all the forces are tension. You're right. That cable, it can't push on anything. But all of this stuff happened because of tensions, because of pulling. Yeah, right. Yeah. So there's sort of there's a funny relationship sort of between velocity and acceleration. Like instantaneously, they're totally independent of each other. It's only if you integrate what the acceleration is happening over time that you get a change in velocity. Like, for example, so it's so at this instant we're going to calculate what the acceleration is, and we know the velocity is, because we described it this way, we know the velocity is to the right. So once we get this acceleration, what's the new velocity of the box? Well, if it's only happening at this instant, that velocity is unchanged. If we keep that acceleration happening for a millionth of a second or a tenth of a second or a year, then there's some resulting velocity from that. But instantaneously, they're independent.
And also, right, I mean, the velocity we were talking about at the beginning is caused by a force that is not in this diagram.
Right, exactly.
In that sense,
Always,
totally
right.
independent.
Yes,
Because the acceleration that we're calculating is caused by forces separate.
exactly.
from caused initial.
That's right. Yep, that's right. Yep. Any other questions about that? Okay, so we got 5 equations now with the constraint equation. 5 equations, 5 variables. The first one says, so I'm just going to go up here. This is the x component of Newton's second law for the 2 kilogram box. T plus 0.2 n is equal to 2a2. The second one says negative 19.62 plus n is equal to 0. The third equation says T minus 0.2 n minus 0.3 n2 is equal to 5a5. The fourth one says negative 49.05 minus n plus n2 equals 0. And the fifth one says a2 equals negative a5.
Those all are 15 Newton
Yes, you're right. I missed that there. Yeah, thanks. So that should be a minus 50 is equal to 5a5. Okay, so how do we solve this system of equations? You could do it by substitution, but we're gonna have enough of these systems of equations that'll take long enough that you're gonna want to get comfortable with another way of doing it. If you have a TI-89, I know there's a really simple equation solver. Otherwise, set this up as a matrix equation. So we can write this as a matrix with 5 variables. Let's see. Okay, so we're going to set up an equation that's a matrix times a vector is equal to a vector of constants. And I'm going to do these variables in the order. The first one is going to be t, then n, n2, a2, and a5. And now each of these columns, so this just has to do with the way, we're going to represent these 5 equations as this matrix equation, where these are all constants. In order to do that, recognize that everything here has to be the coefficients that go along with t. Everything in the second column have to be the coefficients that go along with n. Coefficients of n2, coefficients of a2, coefficients of a5. So equation 1, we have 1 times t plus 0.2 times n. Now we have to rearrange this. Anything multiplied by a variable needs to be on the left side of the equation. So this has to be, in the A2 column, we're going to have minus 2. And are there any constants in this equation? Nope. So everything else is zeros. The second equation, we have 1 times n is equal to 19.62. Everything else is zeros. The third equation says 1 times t minus 0.2 times n minus 0.3 times n2 minus 5 times a5, and then positive 50 on the right side. So this is a 0. The fourth equation says negative 1n, positive 1n2, and the constant is positive 49.05. So these are all zeros. And the fifth equation says 1a2 plus 1a5 is equal to 0. Well, you move this over to the, so anything with multiplied by the variable, move to the left. Anything that's a constant, move to the right. So there's two ways to do this on your calculator. If you call this matrix A, call this list of variables X, and call this vector of constants B, you're trying to solve for the vector X. So X is equal to A inverse times B. And so you can do that on your calculator, first of all. The second way you can do this is write this equation as an augmented matrix, it's called. Which in this case would be 1.20, -2, 0, 0. So write this whole matrix and then add this vector of constants on as an additional column. So the second row then is 0, 1, 0, 0, 0, 19.62. The third row is 1, -0.2, -0.3, 0, -5, 50. Fourth is 0, -1, +1, 0, 0, 49.05. And the last one is 0, 0, 0, 1, 1, 0. And then use, it'll be listed as RREF. So if you call this matrix, say the matrix B, RREF of B will give you the answer. This stands for, do you remember what this stands for?
Reduced row.
Yep, right. Reduced row echelon form. And it'll give you a matrix that's diagonal ones, and then the last column will be your solutions. In the order, whatever order I said, Tn. Do it in a matrix. T, N, N2, A2, A5. That's the easier one to use, the reduced row echelon form. And it's faster if you end up with big matrices. Yep. Yeah. That means that yeah, I think what that means is that your solutions are dependent on on one parameter, which means that this system wasn't solvable. This system is solvable, so I think it's easy to just type something in wrong. I think the answer you should get is, oh, well, I have it wrong because I didn't have that 50. Can I use that, Ryan? Oh, okay. Well, you got different answers? Let me do the tiebreaker. Who has it 89? You have it written down? Yeah. For the tension, we got 18.49 newtons. For the normal force between the two boxes, we got 19.62. Just the weight of the top box, that makes sense. For the normal force of the bottom, between the bottom and the ground, we get 68.67, which is just the weight of the two boxes together. That makes sense. For A2, we got positive 11.207. And for A5, we got negative 11.207. These are meters per second squared. And so we wanted the acceleration vector of the top box. So now take this value. Okay, so take this A2 that we calculated, plug it back into for the 2 kilogram box. This is the acceleration vector for the 2 kilogram box. A20. So our acceleration vector is 11.2070. So the 2 kilogram box is accelerating to the right, which makes sense. Two things are contributing to that acceleration. One is the 50 Newton force, and one is that all the friction forces are acting in that direction on the box, because that's opposite the motion. Any questions about that? To go back to the exam for a second, I said that to get ready for the exam, you should just focus on those practice problems. So those practice problems you should focus on. You also should consider the example problems that we do in class, like more practice problems. You need to understand those. And you also should be, you should look back over the quizzes. I'm going to put a couple of those quiz questions on there. Okay, so those are the things you need to do to get ready for the, so this is embedded exam 1 information. This is, I just do this I use strategery to trick the people who only look at the beginning of my lectures. Not really. So focus on the practice problems. The example problems from class. And just familiarize yourself with the quiz questions. There will be a handful of quiz questions on the test. Okay. All right. Well, that's it for particle kinetics. So that's the end of the stuff that's going to be on the exam. So hopefully, you should have plenty of time to work on that. So now we're going to move on to so that was all particle kinetics. No rotations, and no length. No lengths on the bodies, right? You can have circular motion. With particles. Just no rotation. So what does that mean? Because the circular motion equations are going to come up a lot when we're talking about rigid bodies. And I think it can be a little tricky to separate these two out. But so circular motion for a particle is like this. Look, I'm a particle. Okay? Rotational motion is this. Particles may or may not do that, but we just don't care, And you can combine those two motions, and it looks like this. But so with rigid bodies, we'll have cases where both are going on, like the center of an object is moving in a circle. The object is also spinning around the center, and in that case, we're going to have to do rotation and circular stuff. So now we're moving on to collections of particles. And rigid bodies. And the vast majority of this is going to be rigid bodies. I'm basically just going to say a few words about what we don't know about general collections of particles. So when we talk about things that have size, when we're talking about objects with size, with length, rotation is important. It wasn't with particles. And we're usually going to break motion up this way. Into first an object's translation and now think about the motion of an object that has some size. So think about this thing flying through the air. What's its velocity? Okay. Well, that question doesn't have a defined meaning yet, right? Because the velocity of this point at this instant, its velocity vector is like this, right? At this point, its velocity vector is that way. So what's the velocity? There's infinitely many answers. We're going to usually break this motion down into translation of the center of mass. And we're going to add to that motion then rotation of individual points about the center of mass. Can you think of a reason why we're usually going to look at the translation of the center of mass? This came up in passing when I introduced Newton's second law. There's an important thing, there's an important aspect of Newton's second law for collections of bodies that makes this useful. So this is because F equals ma really is F equals m times the acceleration of the center of mass. And that's always true no matter what collection of particles you're talking about. So this lets us use Newton's second law, and that's why this is a nice way to break things up. Okay, so let's talk about first basically what we don't know about general collections of infinitely many particles. Like a blob of pudding. We do know this. Add up all the forces on your blob of pudding, all the external forces. So choose how much of that blob you want to isolate. Add up all the forces on the outside. Those are equal to the total mass of the blob times the acceleration of its center of mass. Okay, so that's something really useful. That's something useful that we know about pudding. Okay, pudding dynamics is a more advanced class that you'll have to take later in your food sciences engineering programs. So what about the rotational motion? With rotation, you can't say too much that's useful. What you can say involves the idea of angular momentum, conservation of angular momentum. And I'll just define that, but we're not going to talk about angular momentum. But it's usually denoted h. It's only defined for a certain about point the same way like a moment is. And it's equal to a vector rho crossed with the linear momentum. And why can't we say much that's useful? Because the only things we can say involve the angular momentum of each individual particle. And if you're talking about pudding, there's a lot of particles, and you can't sit there and do these calculations for especially if you treat it as a continuum and there's infinitely many particles, you'll be sitting there a long time. So general collections are kind of out, but you can make useful simplifications if you can treat your collection of particles as a rigid body. So before I go on to that, I have a question about Newton's second law here for a general collection of particles. So if you have infinitely many particles and you isolate them all as one thing, and they're bouncing around off of each other, the fact that you only have to deal with the external forces on that collection of particles is hugely lucky, right? Anybody have a feel for why that is, that you only have to deal with the external forces? Like if you had to deal with all the infinitely many collisions going on at the same time, maybe 3 external forces are being applied to this thing, it would be impossible. Yep.
Is it because of Newton's law that said the other law that says
Yeah.
the external forces that change the...
Well, it's because of Newton's third law that says for every action there's an equal and opposite reaction. Since all those collisions are happening inside your boundary, right, you'd add up each of those forces, you know. You'd have to add the force going this way and the equal and opposite force going this way. And so all of these forces that are happening, that one thing's applying to one and one's applying to the other, cancel each other out. The only forces that are left that aren't canceled out are the ones on the boundary that are applied by something outside. You know, because the thing outside applies a force to the boundary applies a force to the outside too, but that's not part of our system anymore, you know.
So we couldn't do this with an amoeba.
You couldn't do the rotation part with an amoeba. Right. Well, I mean, what you would probably want to do is you would probably, an amoeba you'd probably do as fluid mechanics. But what would you do with like silly putty or something, you know? There would be times when silly putty is roughly behaving for some period of time like a rigid body. It's not bending or whatever, or the changes in shape are slow, and you would make the approximation of a rigid body. Or possibly like what you do with people, you know, like the human body, nothing's actually rigid, you know, even the bones aren't. I mean, nothing in the world is actually rigid. But you treat an arm as a rigid body here, a rigid body here, you know. You make that simplification as many times as you can while losing as much, accuracy as you can. And then you apply the rules of rigid bodies. Was there another question?
Well, I just wondered, is that why Newton's first law says that a body stays at rest unless it has an outside force? The word outside.
That's right. Yeah, you're right. Yep. So yeah, even with, I brought it up now because we're talking about all these particles, but everything we've been treating as a particle, you know, and everything that we're treating as a rigid body, actually, there are all these internal forces going on that we've just sort of been glossing over up until this point. But yeah, the outside forces are the only ones that make the isolated body accelerate. Okay, so with rigid bodies, and now we're done talking about deformable general collections of particles. With rigid bodies, you know two things. first, you know that the sum of the external forces is equal to the mass of the rigid body times the acceleration of its center of mass. That's Newton's second law. And second is the rotational equation. So I'll call that rotational Newton's second law. I'll always just abbreviate it as Rn2L. That's derivable from Newton's second law. And we'll think of this as two pretty much equivalent, very similar looking equations. And which one you use depends on the problem that you're dealing with. So first of all, the sum of the moments about a body's center of mass, about the rigid body's center of mass, is equal to the moment of inertia about the center of mass times the angular acceleration. This one is always true. And second, similarly, the sum of the moments about some point A are equal to the moment of inertia of the object about A, and I'm going to have to define what all these things mean and stuff, times the angular acceleration. And this is true only when A is a point on the body that's fixed in your coordinate system. So if this one is always true and this one is sometimes true, why don't we just forget this one and just always deal with the one that's always true? Well, this one, when this one does hold, it makes the calculations a little bit easier. So it'll be in your interest to use that when it's available. Yep.
Does it have to be on the body?
No, but it needs to be fixed relative to the body. It needs to be fixed relative. So if
I was thinking like a donut that has like an empty center where the center of mass would actually be outside the body.
the center of mass definitely doesn't have to be on the body.
Because then like it seems like if A is the center of mass, then they're usually like the same.
Yep, that's right. But let me draw a couple pictures of these kind of problems. And by the way, speaking of center of mass being on the body or not on the body, you know, you ever watched like good high jumpers? They go over the bar backwards. You know, this is his head. Okay, they go over like this. So why do they do that? Like, it doesn't put your body in any favorable position for actually jumping higher. It doesn't make it easier to get your center of mass higher. It's just that this is a way to go over the bar where the good high jumpers, their center of mass is down here, and they can clear a high jump bar without their center of mass ever getting as high as the bar. Isn't that weird? Like at every instant, the part of the body that's right above the bar is over it, but the center of mass, if you track it, just goes directly under the bar. It never blips up over, never gets up that high for a second. So anyways, center of mass doesn't have to be on the body. Okay, so for example, if you had something like this, where this body rotates about this pin at A, in this case, and say the center of mass of this object is here, okay? In this case, you could use either one of these two equations. You know, Rn2L part B, bless you, with the about point at B. Okay, so I have a question about this. I mean, this is going to be a tricky thing. Like, rotational Newton's second law. You're always going to have to be aware of what you can use as your about point for the equation. Okay. Why didn't that ever come up in statics? I mean, statics is just statics is the version without motion of Newton's second law and rotational Newton's second law. So why didn't this ever come up, like being careful about what our about point is and stuff in statics? You can put your about point anywhere you want in statics. Yeah, I mean, the whole idea of statics is everything's in equilibrium, and if everything's in equilibrium, then every point on the body is fixed in your coordinate system, you know? So every point in statics satisfies that second criterion. B, I mean this equation. Oh, that was just because I was trying to write and talk at the same time. About pin at A. Oh yeah, that's wrong. Thanks. On the other hand, if you're doing a calculation, so, you know, this is a boomerang flying through the air. No point on that body is fixed in your coordinate system. No fixed point. So you have to use Rn2LA. So next time what I'm going to do is define all these different values. I'm going to define the center of mass, the angular acceleration, the moment, and the moment of inertia. And then once we have those, we can start doing rigid body problems. Any questions? Okay, that's it.